Hello students, welcome to this lecture on linear prediction of signals. Let us review the Levinson Durbin algorithm. We are given the order of prediction m and the autocorrelation functions rym, m going from 0 to m. First we have to initialize the predictor coefficient hm0 is equal to -1 for all m, and epsilon 0, that is the mean square prediction error, is equal to ry0 for prediction order 0. Now for m is equal to 1 up to m, first we will determine the prediction coefficient km, which is given by summation hm minus 1 I into ry m minus I going from 0 to m minus 1, whole thing divided by epsilon m minus 1, that is the mean square prediction error at stage m minus 1. Then we will update the filter coefficient HMI is equal to hm minus 1 I plus km into hm minus 1 at m minus I going from 1, 2 up to m minus 1. And the last filter coefficient HMM will be updated as minus km. And finally, we will update the mean square prediction error epsilon m is equal to epsilon m minus 1 into 1 minus km square. So, km we have determined here. Let us consider the review example on Levinson Durbin algorithm. Suppose the SCFs of a WSS process are given by this: ry of 0 is 2.89, ry of 1 is 1.51 and ry of 2 is 1.21. Find the second order LP coefficients directly by matrix inversion and applying the Levinson Durbin algorithm. So, solution is like this. We have to first establish the WH equation, Wiener-Hopf equation in matrix form, that is given by this autocorrelation matrix into the coefficient vector is equal to the autocorrelation vector. So, that way here it is ry0, ry1, ry1, ry0, and similarly coefficients are h1, h2. Therefore, if we substitute these values from here, so autocorrelation matrix is 2.89, 1.51, 1.51, 2.89, then multiplied by the coefficient vector h1, h2, and this must be equal to ry1 is 1.51, ry2 is 1.21, and we can directly take the matrix inverse and then multiply with this 1.51, 1.21, and we will get the filter coefficient as h1 will be equal to 0.4178, h2 is equal to 0.2004. In this lecture, we will derive recursive expressions for forward and backward prediction errors using the Levinson Durbin algorithm, and we will use those prediction errors for an efficient implementation of the prediction error filter. We will derive the expressions for forward and backward prediction errors recursively. Let us denote EMFN, that is the prediction error of mth order forward prediction at time n. Similarly, corresponding backward prediction is given by EMBN, that is the prediction error of mth order backward prediction. Clearly, forward prediction error EMFN is equal to yn minus summation HMI into yn minus I going from 1 to m. So, this is the mth order prediction. So, the difference is the prediction error. Similarly, EMBN, that is the mth order backward prediction error. Now, we are predicting yn minus m by this relationship. So, that way the backward prediction error is given by yn minus m minus backward prediction, which is given by summation hm m plus 1 minus I y n plus 1 minus I going from 1 to m. We want to establish the recursive relation between the prediction errors EMFN is equal to EM minus 1 Fn plus Km times EM minus 1 Bn minus 1. Similarly, backward prediction error EMBN is equal to EM minus 1 Bn minus 1 plus Km times EM minus 1 Fn. So that way forward prediction error EMFN is given by the forward prediction error for order m minus 1 EM minus 1 Fn plus Km times the backward prediction error of order m minus 1, which is delayed by 1. So this is a delayed version of the backward prediction error. Similarly, backward prediction error also delayed version of the backward prediction error of order m minus 1 plus Km times forward prediction error of order m minus 1 at instant n. Now we will prove the recursion of prediction error. EMFN is equal to Yn minus summation HMI Yn minus I going from 1 to m. Now we can write EMFN as Yn minus that last coefficient here. I am taking out HMN into Yn minus m. So when we put m here, HMM into Yn minus m, that I am taking it out. And then summation HMI into Yn minus I going from 1 to m minus 1. Now we note that this minus Hm of n is equal to Km by definition. And here we can apply the Levinson Durbin recursion. Applying Levinson Durbin recursion, we get EMF of n is equal to Yn plus Km into Yn minus m minus summation I going from 1 to m minus 1 of now we are substituting Hm I is equal to Hm minus y I plus Km times Hm minus 1 m minus I. So this is the recursion we are using for HMI, which is true for I is equal to 1 to m minus 1, and then whole thing into Yn minus I. So this is the relationship we get from here. Now we can bring these terms containing Km together, so that way Yn minus this will bring here, this will bring here, Yn minus summation Hm minus 1 I into Yn minus I going from 1 to m minus 1 plus Km times Yn minus m minus this term summation H of m minus 1 m minus I Yn minus I going from 1 to m minus 1. Now this part is the forward prediction error of order m minus 1. So this expression will be Em minus 1 Fn plus Km times, now this term is Yn minus m, that is the true value, and this is the backward predicted value. So that way this is the backward prediction error at n minus 1. So that way this will be Km times Em minus 1 B n minus 1, because this is m minus 1th order prediction and prediction starts at Yn minus 1. So that way this is backward prediction at time n minus 1. So that way we have arrived at the relationship that EMF n is equal to Em minus 1 F n plus Km times Em minus 1 B at n minus 1. Similarly, using the backward prediction error, which is given by EMBN is equal to yn minus m minus summation HM m plus 1 minus I into yn plus 1 minus I going from 1 to m. This is the backward prediction error. And now here also we will be using the Levinson Durbin recursion. Then we can show that EMBN is equal to EM minus 1 Bn minus 1 plus Km times EM minus 1 Fn. Thus, we have established the recursive relations EMFn is equal to EM minus 1 Fn plus Km times EM minus 1 Bn minus 1. Similarly, EMBN is equal to EM minus 1 Bn minus 1 plus Km times EM minus 1 Fn. These errors have interesting properties which are very useful for practical purposes. Now, we will derive an alternative expression for the reflection coefficients in terms of the forward and backward prediction errors. Recall that Km was defined in the Levinson Durbin recursion as Km is equal to minus Hm of m. So, if it is a mth order prediction, that last coefficient is with negative sign is Km. Since Km is derived from the optimal LP coefficients, it is optimal with respect to the mean square prediction error. Now, let us consider the forward prediction error, that is EMFn is equal to EM minus 1 Fn plus Km times EM minus 1 B n minus 1. We have E of EMF n whole square, that is the mean square prediction error, is equal to E of EM minus 1 Fn plus Km times EM minus 1 Bn minus 1 whole square. So, this is the forward prediction error, and for Km to be optimal, the derivative of the mean square error with respect to Km must be equal to 0. Thus, we get the dkm of E of Em minus 1 Fn plus Km times Em minus 1 Bn minus 1 whole square is equal to 0. So, we take the derivative. So, it is a derivative of this, and then again inside it is a function. So, that way we will get E of m minus 1 Fn plus Km times E of m minus 1 B n minus 1. Now, this expression, when we take the derivative with respect to Km, we will get E m minus 1 B n minus 1, that must be equal to 0. Implies that Km is equal to minus E of Em minus 1 Fn into Em minus 1 B n minus 1 divided by Em minus 1 B n minus 1 whole square. We can get a similar expression by considering the mean square backward prediction error, and in that case Km can be shown to be like this. So, same value of Km we can either get through this expression or this expression. Now, let us try to interpret the reflection coefficient Km. Km is given by this. The denominator is MMSP and is a normalizing term. Em minus 1 Fn is the residual part of Yn after removing the correlation with Yn minus 1, Yn minus 2, etc. up to Yn minus m plus 1. So, after removing the correlation of the intermediate data, whatever residual is there, that is Em minus 1 Fn. Similarly, Em minus 1 Bn minus 1 is the residual part of Yn minus m after removing the part correlated with Yn minus 1, Yn minus 2 up to Yn minus m plus 1, same set of data. Thus, the numerator, this expression E of em minus 1 Fn into em minus 1 Bn minus 1 is the cross correlation of yn and yn minus m after the correlation due to the intermediate data are removed. Hence, Km is called the Parker or partial correlation coefficient. So, you have removed the correlation because of the intermediate data, and then you are determining the correlation between em minus 1 Fn and em minus 1 Bn minus 1. So, these are the residuals after removing the correlation due to the intermediate data. So, that is why the name is Parker coefficient. Now, we will prove one important result, whiteness of the backward prediction errors. Consider two backward prediction errors. Suppose em Bn is equal to yn minus m minus summation hm m plus 1 minus I into yn plus 1 minus I going from 1 to m. And suppose kth order backward prediction error ek Bn is equal to yn minus k minus summation hk k plus 1 minus I into yn plus 1 minus I going from 1 to k. So, this is for suppose k is some number between 0 and m. Clearly, from this E of em Bn is orthogonal to yn plus 1 minus I lying between 1 and m because of the linear minimum mean square error estimation. And since our k is less than m, so E of em Bn into yn plus 1 minus I will be equal to 0 for all I less than equal to k, where k is less than m. Now, this backward prediction error is the combination of data between 1 and k. Therefore, from this expression we will get that this backward prediction error em Bn will be orthogonal to EKBN for k lying between 1 and m, because this EKBN is a linear combination of yn plus 1 minus I lying between 1 to k. Therefore, expected value of em Bn into EKBN will be equal to 0 for k lying between 1 and m. Thus, the backward prediction error signal is white and is efficient for the compression purpose. Now, let us see the lattice filter realization of linear prediction error filters. A prediction error filter can be efficiently implemented in lattice structure. Consider the recursion relations. Em Fn is equal to em minus 1 Fn plus Km times em minus 1 B n minus 1. And similarly, em Bn is equal to em minus 1 Bn minus 1 plus Km times em minus 1 Fn. The above filter equations can be implemented in a lattice structure as follows, because this is the output of the filter section, that is em Fn, and input is em minus 1 Fn and em minus 1 B n minus 1. Therefore, em Fn is the sum of em minus 1 Fn and Km times em minus 1 B n minus 1. So, this we can write using filter elements like em Fn is equal to em minus 1 Fn plus, this is the delayed version of em minus 1 Bn. So, here output will be em minus 1 Bn minus 1, and that will be multiplied by Km and it will be added. So, that way em Fn is the sum of this signal plus this signal delayed by 1 unit and then multiplied by km. So that way we see that this expression can be implemented by this path. Similarly, this backward prediction can be implemented. EMBN is equal to this delayed backward prediction error, this plus the forward prediction error multiplied by km. So that way EMBN will be equal to this part EM minus 1B n minus 1 because it is delayed here plus EM minus 1 Fn multiplied by Km, and that will give us EMBN. This is a simple implementation because same multiplier is used here and there is a summer here and then this delay unit. Thus, we have seen that this recursive relations can be implemented by this filter section. How to initialize this lattice? We know that suppose 0th order prediction, in that case forward prediction error will be yn minus 0, that is equal to yn. Similarly, backward prediction error also will be equal to yn minus 0, that is equal to yn. Hence, EF0 is equal to EB0 is equal to yn, and this can be the initial input, and the first lattice section will be as follows. So, yn it will be passing through this path, it will be passing through this path, and then when delayed version multiplied by k1 is fed here, we will get u1 fn, and similarly when delayed version and this part yn multiplied by k1 is fed here, the sum will be u1 bn. So that way initialization also we have seen. Therefore, complete filter can be realized by cascading all the sections like this. So, input will be yn here, and then first section output will be suppose E1 Fn and here E1 Bn, and like that suppose last section, because we are interested to find out the mth order prediction errors. So, both forward and backward prediction errors will be obtained by the last section. So, the last section input will be Em minus 1 Fn and Em minus 1 Bn. Thus, we can get the forward and backward prediction errors using this lattice filter structure with yn as the input. So, this diagram shows the lattice filter implementation. The lattice structure has several advantages. It is a modular structure. It can be extended by cascading another section. New stages can be added without modifying the earlier stages. Same elements are used in each stage, that is multiplier and summer are used. So, efficient for VLSI implementation. It is numerically efficient because this Km coefficient, reflection coefficient magnitude is always less than 1. Therefore, quantization error will be less here. The backward prediction errors being white can be efficiently stored in hardware implementation, and inverse filter can also easily be implemented. These are some advantages of this lattice realization. Let us summarize the lecture. The Levinson Durbin algorithm can be used to compute LP coefficients. The Levinson Durbin recursion is used to derive the recursion of the prediction error. These are the two expressions we obtained. The reflection coefficient Km measures the cross correlation between yn and yn minus m after removing the correlation because of the intermediate data yn minus 1, yn minus 2 up to yn minus m plus 1. The backward prediction error EMBN for different m are uncorrelated. That also we established. The prediction error filter can be efficiently implemented in the lattice structure. Looking ahead, so far we have assumed that the random signals are WSS, Whiteness stationary, so that they are characterized by the autocorrelation and cross-correlation functions. The winner filters are time invariant because of the above assumption, WSS assumption. Practical signals are non-stationary and the optimal filter should be time varying. One solution is the family of filters known as the adaptive filter. We will study these filters next. Thank you.